In this video, we're going to learn about phase change. So before we talk about changing phases, we need a recap of the different phases and how they differ from one another. So solids differ from liquids and gases based on the strength of their intermolecular forces. In the case of solids, the IMFs are very, very strong, and so particles of a solid will only vibrate. They'll stay stuck in place and simply shake. Liquid particles, they have weaker IMFs, and so the particles will pass by each other. They flow freely. However, as they flow past each other, they stick to an extent, and that's why liquids still remain in a relatively condensed state. But once particles become gases, well, they experience little to no intermolecular forces, and that's why the particles just go out freely. They occupy whatever the volume is of their container. They are not condensed. Um, and ideally, they experience no attraction to one another as they collide. Real gases might experience some IMFs, but they're still quite weak. And that's why, because the particles are moving so fast, they don't quite really stick to each other and then fall into a more condensed phase like a liquid or a solid. So, how does melting and boiling occur? Well, imagine this. We have some ice and it's at negative 20 degrees Celsius, and the particles are vibrating in place. And that's their kinetic energy. It's manifested in this vibration. Well, as heat is added, the temperature rises from negative 20 to negative 15 to negative 10, and eventually it gets to zero. At that point, at 0 degrees Celsius, the kinetic energy of these vibrating particles exceeds the potential energy of the hydrogen bonds that holds them together. And as a result, they start to separate. And that's when melting occurs. You could say similarly, as water in the liquid phase gets hotter and hotter and hotter, the particles are flowing past each other faster and faster and faster, yet still experiencing some hydrogen bonding. Um, but once they hit 100 degrees, then they are free to flow out in all different directions. And that's because at that temperature, the kinetic energy of these water molecules moving around is greater than the hydrogen bonding strength that's holding them together. So we also need to understand in the topic of phase change that it is an equilibrium process. It is a reversible reaction, of course. Anything that you can evaporate, you can condense. Anything that you can melt, you can freeze again. But a certain amount of phase change will happen even before you reach the melting point or boiling point for that matter. So let's consider a bottle of water. Everybody has seen a bottle of water with these droplets condensed higher above the actual level of the liquid water. You might wonder how that works. Well, every liquid has a certain amount of what's called vapor pressure. And vapor pressure is essentially the amount of the liquid that actually evaporates into the gaseous phase. So there will be an equilibrium at any temperature where some of that liquid is in the gaseous phase. And of course, at lower temperature, there's going to be less liquid that is evaporated. But the hotter the liquid becomes, the more vapor pressure there is. And in the case of your water bottle, the hotter your water bottle is, the more condensation you'll see. Consider the difference between, on a cool day, you have a bottle of water outside. There's not going to be a lot of condensation, but on a hot summer day, that condensation forms quite quickly, and there's quite a bit of it. At equilibrium, it should be noted, the rates of evaporation and condensation do equal one another, but that equilibrium is established at higher temperatures. It's established favoring more and more of the gaseous phase substance. And actually, here we have a graph of water and its vapor pressure at different temperatures. So you can see at 20 degrees Celsius, there's not a whole lot of vapor above the surface of water. But as temperature rises, eventually, when we hit 100 degrees Celsius, the vapor pressure is equal to atmospheric pressure. And what's interesting there is that the boiling point is the temperature where the vapor pressure has climbed so much that it is equal to the atmospheric pressure. So, on the topic of vapor pressure, there are differences among different substances. We know that water has a very high boiling point relative to ethanol or diethyl ether, and that's owed to the great strength of hydrogen bonding in water. Ether has not even really a dipole moment at all, so it only really experiences London dispersion forces. Well, as you might imagine, in addition to substances with weaker IMFs having a lower boiling point, they also will have a higher vapor pressure, meaning that at any given temperature, a substance with weaker IMFs is going to have more of it in the vapor phase. And of course, it will reach that atmospheric pressure with its vapor pressure. They will meet at a lower temperature. And that's what we're seeing here with diethyl ether at, say, 0 degrees, where there's basically no vapor pressure for water. There's already about 200 millimeters of mercury of pressure for the diethyl ether, and then it just rises from there, reaching atmospheric pressure, the boiling point, at 35 degrees Celsius, whereas water at 35 degrees Celsius as well still is around even less than 50 millimeters of mercury. And so that's a difference there. So always, when considering different molecules' polarities, you can make predictions as to their vapor pressure and their boiling points. The weaker the IMFs, the higher the vapor pressure and the lower the boiling point. Anyway, I hope this video has helped. Please feel free to leave any questions or comments in the comment section below. Thanks for watching.